Here we go, part 3 of our practice SAC questions. Something to entertain you on the Sunday morning. Here we go. Alright, so we have this question. The velocity time graph below shows the velocity of a lift as it travels from rest to the 12th floor of a tall building during 2 seconds of its motion. Very good, pretty graph. The velocity at time t seconds from 0 to 2, okay, is given by this function, okay, v equals t squared times 3 minus t. Now, I've underlined that because really that is the most important thing to consider. The rest of it, after the first 2 seconds, the lift moves with a constant velocity 4 meters per second for a time and then decelerates to rest in the final 2 seconds. Acceleration of the lift is a. The velocity time graph is symmetrical about t equals a half t. There's a lot of information there, and we got to ask ourselves, is it really that important? And let's look at the question. Part A. Express a in terms of t for the first 2 seconds of the motion of the lift. Alright, so we really are just focusing on this part of the graph only. That's what part A is only pertaining to, only for the first 2 seconds. So all the rest of the information describing the graph and the graph itself, really it's kind of a bit of a redirection and trying to confuse you a little bit. That's nasty. Alright, let's keep going. So first off, we have the acceleration. So to find the acceleration, we take the velocity function and we differentiate with respect to t. And we can do that using the chain rule. So that's u times v dash plus v times u dash. And we get this function in its simple form. Okay. And it's quite straightforward function. It's a quadratic. I'll just put the thing on the t there. And we're pretty much done for that question. We just state it nicely at the end and we will get our mark. Okay? Now, I just wanted to bring your attention here to the graph. That point there is an interesting feature of the graph. It's called a point of inflection. And it is a point where the gradient of that slope is the most steepest. So let's just highlight that and consider that for a moment. Let's look at the next question. So, hence, find the maximum acceleration of the lift during the first 2 seconds of its motion. So when we see that term, hence, when we see that term hence, that means use some result you got from the previous question and to help you answer this one. Now, thinking about the maximum acceleration is kind of like that. It's that point of inflection on that graph. It's the point where the gradient, the steepness of the graph, be it acceleration in this case, it's the point where that is the largest, the maximum. So this is what we're looking for. And the idea to find points of inflection is the second derivative. So we take our velocity graph and we have to differentiate twice to find the second derivative when that is equal to 0. And this will give us our point of inflection. Okay, so we differentiate the acceleration function that we used from the first part, and we're drawing on the answer from the last question to help us answer this question. We're going to differentiate it one more time. We get a nice linear thing. So then the maximum acceleration occurs when this derivative is equal to 0. And we get t is equal to 1 second. So that's right in the middle. Symmetrical. This is the whole idea of the graph being symmetrical. So it brings your attention to the fact that, okay, if it's symmetrical, then I can find a point of inflection where we have either side of that point of inflection is the same kind of graph. It must be some cubic expression of this point of inflection. Alright, so having found that, we're going to take this time, t equals 1, we're going to substitute it into our acceleration function, and we're going to evaluate. And we get the value for the maximum acceleration, 3 meters per second. Okay? Very good. Next. Slow it down. Okay, so let's read the question. Question 4, the position of a body at time t is given by this position vector function. I and j are horizontal. Orthogonal means that they're at 90 degrees to each other. Okay? So they're 90 degrees perpendicular unit vectors, and k is a vertically upwards unit vector. So think of I and j is covering the space on the ground, k is going up into the air, and we're interested in finding the horizontal speed of the body. So horizontal speed, first off, let's work out the speed. The speed is given by first finding the velocity vector, first derivative of the function. We get this one that we've differentiated there, and we've got I dot. Now, to find that horizontal speed, we're going to take just the horizontal components. Okay, that's this part only. That's the horizontal part. K is going up into the air, so we're not interested in that. Okay, now the speed is taking the magnitude of the horizontal components only. We get 2 meters per second. Very good. Part B, find the minimum speed of the body. Okay, now minimum speed is going to be a situation where we've got two types of speed. We've got this constant horizontal speed that's not changing. It's always, regardless of what the value of t is, horizontally the speed is a constant. Okay, then you've got this vertical speed. So this part here is the velocity in the vertical direction, and of course if we just look at that, take the magnitude of that, it will be the same function, and you can see it's quadratic, so it's a varying speed. So if we just look at the speed in the vertical direction only in k, then with respect to time, if we look at the function, okay, it's it's kind of like a quadratic. Okay, so given that, upside down quadratic, here we go, it might look a little bit like that at some point in time there, that is at t is equal to 1, and at the point at the very top of there, we have a situation where vertically, this is for position. I shouldn't say speed, should I? Because it's not really the speed that we've just graphed. We've just graphed the position. That's r in k. And at the very top, some vertical position, we've got a velocity is equal to 0 at the very top. So if we can think of the minimum speed occurs when the velocity in k is equal to 0, and we'll see what we get. So we're going to find now the minimum is going to occur when v is 0 in the vertical direction. So that's the derivative of just the k component, and we equate that to 0. And we get t is equal to 1 second. Okay, so there is your minimum speed for time. Now we substitute that into our vector velocity vector function, and we take the magnitude, and we'll find it's again 2 meters per second. So when vertical speed is 0, the only thing that's left is the horizontal speed, and this is indeed the minimum speed for t is equal to 1 second. Okay, so you have to break it down and just look at components, one component or two components at a time. You don't have to consider the whole lot. You're allowed to just, considering the physical situation, pull it apart a bit and just focus on one bit at a time. Alright, part C, find the acceleration of the body at t equals 1 second. Well, this is the r dot dot, second derivative, and we get negative 9.8 in the k direction at t equals 0. Should be t equals 1. Okay, and the acceleration is just 9.8 meters per second vertically downwards, because we've got a projectile motion situation. So regardless of what time it is, in fact it could have been t equals 10 seconds, we will have still an acceleration of 9.8 meters per second. Fantastic. Okay, well, that is that question done. Next bit. Now, we did have another question, question 3 on the task. Now, I'm going to leave that question for a little bit, and we'll come back to it another time. I'll put a separate video just for that one because it's a big question. But the question itself was slightly erroneous, and it would be an interesting activity to identify what's the problem with it. Okay, but first off, let's focus on this one, which is question 4. So we've got the velocity of a particle moving in a straight line is given by this velocity velocity function with respect to t. Find the time when the particle comes to a stop momentarily. So it implies that it doesn't stop for a long time, it stops for just a split second in time. So we're looking at some continuous movement, some continuous graph. Okay, so when the particle comes to a stop, we've got a velocity of 0. So there's our starting point. We're going to let v equal 0. We let the function is equal to 0, and then we're going to solve for t. And we find that only occurs when the numerator is equal to 0, not the denominator, because if the denominator is equal to 0, we're in trouble. When the numerator is equal to 0, we get t equals a half second. Okay, straightforward, that one. Now, I want to bring your attention to a little bit more about this graph, this function and its graph. So, the job is to find the exact total distance of this particle at t equals 1 second. Now, first off, let's try and explore what this graph looks like. If you do this on the CAS and do it as a graph from 0 to 1, it'll look, and zoom in, it'll look a little bit like that. That's what you'll get on the CAS. And as you can see, we've got two parts there. We've got a positive area part, and we've got a negative area part. Okay, and the area under the graph is your distance traveled. Okay, so how do we handle negative area? Okay, that's what we have to ask ourselves. It is found by doing the subtraction. Okay, subtracting the area that is negative in order to get the total area enclosed by the graph, which in this case it's the total distance traveled. Okay, now for us to work with this function, it's not really pretty. It's not in a good form we're used to. So we're going to rearrange it a little bit. And first off, we will see, I'm going to expand that 5 into the bracket. And then I'm going to add terms. I'm going to minus 5 and then I'm going to add 5. Now, the reason why I've done this is to manipulate my function a little bit. And you'll see what it does. I'm going to collect the minus 5 with that minus 10t. And what's left is just the plus 10 from the two positive 5s. And now I factorize this negative 5 out, and I've left it with a bracket factor that's the same as the denominator. Now it's very good because I've got a common factor that I can cancel. And I get that. And this here is a hyperbola function, rectangular hyperbola. Looks a little bit like that. And you can see the positive region of the little Cartesian plane. Looks very similar to the black graph there. Okay? So that's the same graph. It's correct function, but it's in a form now that helps me to integrate. And that's precisely what we're doing next. To find the total distance, it's the integral, okay, of our velocity gives distance. So we need to carry out an integral in such a way that first finds the area of the positive region of the graph from 0 to 1/2. That's the first integral there. And then the second integral is subtracting the integral from 1/2 to 1 of the same function. Okay? So that integral expression there will give you your total distance. Okay? Now at this point in time, it's a CAS active task, so you can use your CAS to evaluate that, but what you do need to do is just do a couple of lines of working out to show that you can carry out the integral. Alright, this is your method. So first off, taking out that factor allows you to show I've got the fraction in a form where you have the derivative in the numerator of derivative of the function that's in the denominator. Now when you've got derivative of function divide function, that is a special form, and the integral of that is a log. Okay? So you integrate using CAS, and then we can go ahead and evaluate this on this thing here on the CAS. And we will get that as your result, 5 times log of 4 on 3 meters. Okay, that does not need to be evaluated by hand. It's a CAS active task, and that can be done under CAS. Excellent. Okay, now this is the last question. It's quite straightforward. Okay, the position vector of the helicopter from the origin on ground level at time is given by this position vector, where I, j, and k are unit vectors east, north, and above point O respectively. Alright, so it's just trying to give some physical direction to each vector, unit vector. And then there's another helicopter. We've got helicopter flying around, given by this position vector. Our job is, part A, find the original positions of the helicopters and their initial distance apart. So original positions occur when time is 0, at the start of everything. What is their position at time is 0? So substitute t equals 0 into each, and you work out r1 of 0 and r2 of 0. Okay, and then the distance apart is given by this rule. You r2 at 0, subtract r1 at 0, and then you take the modulus of it to get the length of that vector. So we're going to carry out the subtraction of vectors and then take the modulus of it, and we will get root 26 units. Okay? Good. And part B, find the position of the helicopters at t equals 1 and their distance apart at this time. Well, same same similar question, but now we're just doing it at a different time. So you work out the position vectors for t equals 1. You subtract r2, take r1, and simplify, take the modulus of it, and we get that result, square root of 42 units. And yeah, it's done. So we're going to stop there, and I hope that's been helpful. We're going to look at that other question I mentioned shortly, and hopefully this has been helpful. Please study and ask me any questions that you're stuck on. Thank you very much.